So we're looking at crystal structures. So we talked about three different types of cubic crystal structures. We have the simple cubic, we have the body-centered cubic, and we have the face-centered cubic. Okay? Simple cubic means that the atoms touch along the edge of the cube. Body-centered cubic means that the atoms touch along the body diagonal of the cube. Yeah. So there would be one in the center here, there'd be one here, and there'd be one back here. But they'd be big enough that they touch along that diagonal. Okay? Face-centered cubic means that there's one in the middle of the face of the atom here, on the edge of the cube. There's one on the corner here, and there's one on the corner here. Right? So in all cases, there's always going to be an atom on the corner of the cube. How many corners of a cube are there? There's 8 corners, right? So there's always going to be 8 corners, but that corner is shared with 7 other cubes, so each corner is only 1/8, okay? So if we have an atom centered on the corner, it's shared with 7 other cubes. So there are 8/8 of atoms on the corners. How many faces are on a cube? There are 6 faces on a cube. Now think about stacking a cube on top of a cube or a cube next to a cube. If you have an atom centered on the face of one of those cubes, it's going to be shared by how many cubes? 2, right? If we've got a plane right here and I've got an atom sticking in it like that, this cube sees half of it, this cube sees half of it, right? So we have 6 faces, but each face only contains half of an atom. So we can get 3 atoms from faces. What about the body? Well, we can have 1 in the body, and if it's in the body of the cube, it's not shared with any other cubes, right? So how many atoms do you think would be in a simple cubic cell then? You know, only 1 atom here. Because there are 8/1/8, because there's only atoms on the corners in a simple cube. All right, what about body-centered cubic? You got atoms on all the corners here. And you got 1 in the middle, right? So how many do we have here? You got 8/8 for the corners plus 1 in the middle. That's 8/8, Josh. So how many total? 2 atoms total. Now what about face-centered cubic? Well, we got 6 faces, each giving us half an atom. That's 3. And then we got 8 corners, each giving us 1/8 of an atom. And that's 1. So we got 4. Four atoms in a face-centered cube. We also have relationships between the length of the side of the cube, which we call the lattice cell parameter. So if we have a cube like this, we call this over here A, the length of the edge of the cube. And we can relate that to the radius of the atom. But that relationship depends on how the atoms touch each other. In a simple cube, they touch along the edge of the cube. In a body-centered cube, they touch along the diagonal of the cube, the body diagonal, right? From the top front left to the bottom right back corner. For a face-centered cube, they touch across the face of the atom, or I'm sorry, the face of the cube. So we can make those relationships. In simple cube, the lattice cell parameter is just 2 atomic radii. Since the atoms touch along the edge of the cube, that makes sense. For face-centered cube, we got to do a little math. We know that the lattice cell parameter squared plus the lattice cell parameter squared is going to be equal to that diagonal squared, right? This is a Pythagorean theorem. That's a diagonal. That's a right triangle. But how many radii are in that diagonal? Well, there's 2 radii from that one that's in the center of the face, and 1 radii from each one on the corners, so that's 4 radii. So this is going to be equal to 4 radii squared. So we need to find the relationship. So this becomes 2a squared is equal to 16 r squared. Or a squared is equal to 8 r squared. Or a is going to be equal to, what's the square root of 8? Well, that's the square root of 4 times 2, so that's going to be 2 root 2 r. The body diagonal is a little more complicated to work out here, because now our triangle is the triangle that's made from this body diagonal here. Let me do it in red. The body diagonal here, the length of the side here, and the face diagonal here. Right. So we got to do a little more math, a little more Pythagorean theorem to get this relationship. So you're still going to have 4r squared along the body diagonal. You're going to have a squared for this side over here. And what is this face diagonal right here? You're the math person. Well, isn't it a squared plus a squared equal to that thing squared? Isn't that the Pythagorean theorem that we just did for the face? So that length, let's call it, I'm going to call it L right here, okay? So a squared plus a squared equals L, or 2a squared equals L, or a is equal to L over 2 to the 1/2 power. Do you agree with that? That's L's. Do what now?
Why is it L over?
This should be squared actually right there, right? A squared plus a squared equals L squared. So we got to rework. That's my bad. So this is 2a squared is equal to L squared. And so L is what we're after. L is equal to 2a squared, take the square root. or root 2a, right? Is that right? Do you agree? Math person? Yeah, you're good? Keep me honest here. I'm making this up as we go. So now we can say a squared plus L squared equals 4R squared. So we can say a squared plus L squared is already 2a squared is equal to 4R squared. Or 3a squared is equal to 4R squared. Or a squared is equal to 4 over 3 R squared. Or a is equal to 2 over root 3 R. And this is our relationship between the radius and the lattice self parameter for body-centered cubic.